crowded. Big problems demand even bigger solutions. It's a new era for engineering. We can build our way out of anything. In Houston, threatened by hurricanes and heat, a city-sized dome would protect millions. This is Mega Engineering.
Suburbs. We're expecting she'll work her way up to a Category 2 hurricane with winds up to 102 miles per hour and 6 to 9 inches of rain. Of course, if you are in the dome, you're in luck. Another beautiful day with a carefully regulated 72 degrees and just 10% humidity.
Houston, Texas, the country's fourth most populous city, is in peril. Houston has always been vulnerable to killer hurricanes. From the Great Storm of 1900, the deadliest in U.S. history, which killed 8,000 people, Hurricane Ike in 2008, which caused nearly $10 billion in damage and forced the city center to shut down for nearly a week. And it's not only hurricanes. Searing heat and humidity also oppress this great city. On nearly 100 days each year, the temperature climbs above 90 degrees, which in muggy Houston feels even hotter. Air conditioning provides relief, but at a cost. Houstonian soaring electricity use has nudged the city ahead of Los Angeles in the race to become the country's #1 producer of greenhouse gases. Houston finds itself square in the path of an environmental juggernaut, which threatens to make the city unlivable. That's why some think that the only way to save Houston is to move it indoors. The plan? Put the entire city under a massive dome. 1,500 feet high, 1 mile in diameter, a 3.1-mile base, circling Houston's downtown offices, apartments, and parks, where millions live, work, and visit each year. A bold dream that requires engineering on a scale never before attempted. Billions of dollars. Hundreds of thousands of tons of steel. Advanced transparent materials, gossamer thin, yet sturdy enough to withstand hurricane force winds. And above all, radical new construction methods to create the world's biggest megastructure over the heads of millions, safely, with minimal disruptions. It's not as crazy as it sounds. There is a precedent. In Cornwall, England. It's called the Eden Project, but despite the name, this storied site was once anything but paradise.
This used to be an old China clay pit. For about over 100 years it's been mined, so they've created this massive hole in the ground, and it was reaching the end of its life.
The project was the brainchild of British record producer Tim Smith. His dream was to turn the old open pit mine into a dazzling botanical showcase representing diverse global climates. But building an enclosure for an array of tropical and Mediterranean plants in Cornwall's temperate climate would stretch the very definition of a greenhouse. Building a traditional box-shaped greenhouse on the site would not have been efficient. It would have wasted materials, space, and energy. An unacceptable compromise with Eden's green mission. So builders had to think outside the box. Literally.
They wanted to show a large collection of plants, so they wanted to try and find the most efficient means for doing that in this old pit.
A better solution came from architect Sir Nicholas Grimshaw, who offered a design based on the work of the visionary, quirky genius, Buckminster Fuller.
Buckminster Fuller was an architect, an engineer, an inventor. He spent most of his adult life trying to educate human beings on the potential of responsible design to remake our world in ways that provided more and better life support for all of humanity.
He's really a polymath, I guess is what you would describe him as. You know, he had an intuitive knowledge of science, math, physics, even though he wasn't trained as a mathematician or an architect or an engineer. It just was in him.
Fuller's multidisciplinary approach helped him in his quest to design a structure that would combine beauty and efficiency in a new way.
He went through a number of different designs and thoughts and ultimately came up with this very simple question. What is the most efficient way to enclose space with the least amount of material and do the most amount of good?
His answer? A dome. As a section of a sphere, a dome is a highly efficient shape for large spaces.
If you want to enclose in a maximum volume with a minimum surface, the sphere is the most efficient geometric shape to use. To enclose the same volume using a square, you need more material than if you were trying to do that with a spherical shape.
But building domes is tricky. Classical domes, like Brunelleschi's dome in Florence, are much thicker at the bottom than at the top. Scaling up to cover Houston would require a base so massive that it could never be built. Fuller wanted to change domes. He wanted to update them, bring them to the masses. In 1954, he submitted a patent application that he believed would usher in a new way of thinking about architecture. He called it the geodesic dome. It solves the big problems of classical domes. Geodesic domes are fully scalable. They're lightweight, super strong, and they can be built out of just a handful of repeating shapes. And in 1965, Fuller floated the most ambitious, some say outrageous idea of his career. A massive geodesic dome covering Midtown Manhattan. Fuller's idea was largely written off as the stuff of science fiction.
When he proposes putting a dome over Manhattan, he doesn't for a minute think this is going to be done by the end of the decade or anything like that, if ever. He meant it to surprise us, to wake us up, to think about what really is possible.
Today, a city-sized dome may finally be possible. Not only that, for some cities it may be necessary to stave off disaster.
We do have these huge sort of, storms that come in and destroy, so much of a city, the whole infrastructure and, the power network. The city just shuts down.
The Houston Dome will begin where the Eden Project leaves off, applying many of the same lessons, but on a vastly grander scale. 91 times the size of its British cousins.
The construction of the dome is going to be a massive undertaking, and yes, it's going to be expensive. But if you think about the lifespan of this dome and what it's going to do for the city, the cost that it's going to save both in energy and the protection of each individual home, it will pay for itself.
A dome over Houston. It's an experiment without precedent. If it works, it will change the face of modern cities forever. But as Houston undertakes the challenge of building the most ambitious construction project in history, engineers could open up a Pandora's box of disasters. There's only one legitimate template for a dome over Houston. It's in Cornwall, England, and was built in 2001. Before the Eden Project, no one had ever attempted to build lightweight geodesic domes on such a grand scale. And almost immediately, the pioneering builders ran into a surprising engineering problem. How to build a foundation that would act less as a support and more as an anchor.
With most buildings, you have to make sure that they stay up. But for us, it was making sure that the biome actually didn't blow away.
Preventing a building from blowing away is not a typical engineering problem. Most foundations are built to prevent a heavy building from sinking. But geodesic domes have properties unlike any other structure, and they follow different rules. It all comes down to air pressure. The buoyancy of megadomes was a problem Fuller anticipated.
Buck used to talk about the possibility that as you created very large geodesic domes, the ratio of the surface area to volume would be such that the air inside the dome would actually have considerable weight, and that if that air was heated up, it could be enough different from the outside air that it would be able to have the whole dome float away.
Engineers at the Eden Project took great pains to secure their domes, to prevent them from lifting off like giant hot air balloons.
We had to build this massive foundation ring all the way around to the bottom of the biome with huge land anchors going deep into the ground to make sure it didn't actually take off.
The ring does another job as well. It acts to neutralize a force that structural engineers call horizontal thrust. It's not like the thrust of a rocket. Rather, it's the tendency of the domes to want to spring open and flatten out. The tension ring built for the Eden domes is a 1,115-foot foundation with over 6,000 tons of concrete. The Houston Dome's tension ring would be vastly larger. 3.1 miles around. Building it would require almost 300 million tons of high-strength concrete, consuming 10 years' output from hundreds of cement factories.
It is somewhat ironic that that important part is going to be buried on the ground and nobody will ever see it.
Though the tension ring is hidden from view, the dome's most remarkable feat of engineering is fully visible. Hundreds of repeating hexagons create a kind of visual rhythm. But behind a geodesic dome's aesthetic appearance lies a hard-nosed geometry. It's no accident that these eye-pleasing hexagons form the structural core of the dome's surface. Because regular six-sided polygons are one of the most efficient shapes in nature. Just look at a honeycomb. But building a dome out of these shapes presents a problem. A surface made out of hexagons cannot follow a curved path.
If you just use hexagons, though, you would just have a flat slope. So every now and again you have to put in a pentagon, which gives it the steer.
With the right number in the right places, a honeycomb can become a sphere. Whether it's the size of a soccer ball, the Eden Project, or the massive Houston Dome, there's one rule that holds constant.
Any geodesic dome has to have 12 pentagons. Okay, that's just a must in order to do it.
Once clued into the secret of the pentagon, it's hard not to try to pick out the rare but critical five-sided panels. Perhaps even more hidden is another construction element. And it provides rock-solid strength. It's the space frame. Narrow steel struts form a geometric web just beneath the surface. The space frame relies on the inherent strength of another shape, the triangle. With tetrahedrons jutting out to the corners of the panels, providing a rigid backstop against high winds.
The triangle holds its shape all by itself. It's inherently self-stabilizing. Now, I can have a network of triangles such that they leave hexagonal spaces in between, and the network of triangles will stabilize the hexagons, which wouldn't be self-stabilizing all by themselves.
Houston is home to 2.2 million residents. Many will soon find themselves on one side or another of a dome that's over 8 times the height of the Eden Project. Of course, in Texas, bigger is always better. As ground breaks on this massive public works project, Houstonians will witness the beginnings of the most ambitious engineering experiment in history. They'll also witness disruptions to daily life, the likes of which no city has ever seen. And as the dome rises over the skyline, the city will have to get used to potentially catastrophic disruptions to life on the ground. When the Houston Dome steel framework begins to rise over the city, construction will resemble that of a steel frame skyscraper. Beams lifted by crane and bolted into place by ironworkers. But the similarities will soon end. As the dome curves towards its apex, crews will find themselves working at dizzying heights over a densely populated city. They'll be assembling nearly 150,000 panels, using almost 1 million struts, joined by hundreds of thousands of connecting nodes.
Building this dome will require a new level and a new methodology of construction.
If you're off by, say, a 1/16 of an inch in one part of the geodesic dome, that'll magnify around and come back, and 2 struts will be 2 inches apart on the other side of the dome. We're talking about the tolerances of the aircraft industry rather than the tolerances of the construction industry.
But how will all these precision machine parts get where they need to go? Hundreds of feet above the heads of Houstonians.
We can use crane up to a certain limit. There's the possibility of putting cranes in strategic locations where we can reach certain areas of the dome. But there are buildings there. There are people living there. So there are places where we cannot place cranes. One of the difference with a dome construction from a typical slab and beam construction is that the dome is not stable until it's finished. Until we have a complete dome shape, the dome will fall apart.
The Eden Project faced and solved the same problem, and turned to a method used throughout the ages in dome construction.
We had to put up what was the world's largest indoor scaffolding, verified by the Guinness Book of Records. So they had to build this massive piece of scaffolding which could then support the structure that holds the hexagons that form the bions.
Building that scaffolding was a project nearly as ambitious as the domes themselves.
To build the Eden Project, we had to build a building to build a building.
But the Houston Dome has a further problem. Here, life must continue as construction takes place overhead. Holding up the dome from below with scaffolding is impossible. So Houston will take the opposite approach.
One idea that's been floating around is to have this army of dirigibles that are capable of staying in place for a long period of time.
Airships hovering over a city recall an earlier era. But a ship like the Zeppelin NT could also be the future. Airships may be lighter than air, but they are also incredibly strong. And today, safe. The hydrogen that filled the Hindenburg was treacherous. But these ships are filled with helium, an inert gas that cannot burn. One of these fuel-efficient ships can stay aloft for hours. And carry a 4,100-pound payload. An army of next-generation ships could take the place of cranes to hold the Houston Dome erect as it nears completion.
It's going to have to be programmed so carefully, every single detail, to ensure that it all runs sort of smoothly.
One false move could spell disaster. Unless builders deploy the world's largest safety net as a final measure of protection. The Houston Dome's surface area will stretch over 21 million square feet, making it the biggest structure with the largest roof in the world. The dome's broadest panels will be 15 feet across, with over 147,000 of them covering the city of Houston. Imagine the nightmare of trying to fill those panels with traditional building materials.
A dome of this size could not be done with conventional materials. If we have to do this in glass or plexiglass or any other of that type, it'll be so heavy that we simply could not build it.
The Houston Dome's panels require something much lighter. Here, in the small German city of Bremen, this factory, the main headquarters of the Vector Foil Tech company, is at the epicenter of a revolution in material science. The company manufactures ethylene tetrafluoroethylene, or ETFE. It's an incredibly strong, yet lightweight and transparent polymer that's changing the face of modern architecture.
Anything that people thought about 20 years ago was based on glass, and it was limited to the technologies of glass. Nowadays, ETFE has basically opened the minds of architects and engineers to completely new horizons.
ETFE is the breakthrough that will finally make Fuller's city-sized dome possible. One of the German company's biggest commissions was the Eden Project. More recently, ETFE was used to create the beautiful bubble-like exterior of the Beijing water cube.
It is so light, 99% lighter than glass. I mean, that's tremendous.
If one is realistic, if one did not go to a lightweight material, the problem of a Houston dome could not be coped with.
But perhaps the real genius of ETFE is in its ease of manufacturing. The material enters this factory as giant sheets of plastic foil. A computer-controlled plotter cuts customized sections to exacting standards.
We have 5-foot strips, which we then shape into whatever size is required. Technically, there's no limit.
The most critical step is the heat welding of one foil to another. A weak seam can lead to tearing, so each foil is welded by hand. The Houston Dome will emulate a feature perfected at the Eden Project. Instead of individual sheets of ETFE, the panels will each be comprised of 3, welded together to create an air-filled pillow.
The ETFE pillows are made up of 3 layers. 1 layer through the center, and then 2 layers surrounding it, which are permanently inflated so that it provides fantastic insulation.
The pillows insulate the domes without adding weight, and most importantly, without decreasing the amount of light that gets through. One strip of ETFE is strong, but 3 layers are even tougher. Not only that, but the cushions can be inflated to create aerodynamic shapes that react to shifting wind loads. Wind forces will subject the ETFE to tensile or stretching stresses. To test this batch, technicians suspend 551-pound weights from a piece of ETFE. To pass, the ETFE should slowly stretch, but not tear. In Houston, an ETFE-clad dome would have to deal with more than just high winds. Scorching heat will beat down on the dome's surface for weeks, if not months, on end. But ETFE can take that kind of punishment and more.
High temperatures are easy to cope with.
Using a propane torch, technicians slowly raise the temperature of a taut sample.
Where most cheap plastics have a melting point around 70 degrees Celsius, fluoropolymer foils have a melting point of about 270 degrees Celsius.
Only by directly pressing the hot blowtorch into the plastic does it finally give way. Of all of ETFE's qualities, there's one in particular that would come in handy in terms of maintenance.
It's a first cousin to Teflon, which means that dirt will just kind of slide off of it, so it's very, very efficient as far as dirt is concerned.
Again, the forerunner of the Houston Dome led the way.
The biomes have been in place for 8 years now, and not once, either inside or outside, have we ever cleaned them. They are completely self-cleaning.
Houston's 50 inches of annual rainfall will allow the dome to be largely maintenance-free. And for those times when repair work is necessary, there's a quick fix.
ETFE foil systems are very easy to repair. They're difficult to break, but once there is a puncture for whatever reason, one just cleans the environment of the hole and takes a little bit of transparent tape, sticks it over the hole, and off you go.
Repairing the dome is no more complicated than sending specially trained rope climbers up to pinpoint trouble spots. It's also safer. Suspending glass over a major metropolitan city would be the mother of all Chicken Little scenarios. Not so with ETFE. If a piece were to come loose,
when foils get detached from the structure, they fall down like a leaf in the wind. They will not hurt anyone, but just drop down safely.
Safe enough and light enough to put over the heads of Houstonians. The material is here. The factory is ready. It's just a matter of pulling the trigger.
To build the Houston Dome is not a technical problem. It's about 5,000 tons of material. We're talking about production capabilities and technologies which are practically available, and they just have to be enlarged by probably a magnitude, and off you go and do it.
As the last of the panels is locked into place, Houston will begin a new chapter in its history. Perhaps the most unprecedented era in the life of any city worldwide. But will it live up to its promise as a shield against disaster? After years of construction, at times trying the patience of Houston residents, the day will come when the final pieces of the dome are locked into place. But the celebration that would follow the successful completion of the dome over Houston is tempered by worry. The original dream that a city-sized dome would protect Houston from nature's ravages was pure theory. Now builders will learn whether their audacious structure will actually make life better or prove to be the greatest work of folly in the history of engineering. Well before nature puts it to the test, residents will have to come to terms with the dome's impact on daily life.
Having an enormous geodesic dome over an urban area would create a new barrier, but there's no doubt there would be a very real distinction between living inside the dome and living outside the dome.
From the outside, the biggest change would be the view. The dome will become a striking and unavoidable new feature of the skyline. But step across the border and that perspective will be lost. From within, it will be nearly impossible to see the dome in its entirety. Buildings will obstruct the view, and as it arcs overhead, trying to make it out against the bright sky will be difficult.
Of course, you'd see it at ground level, but the higher up you got, it's a very delicate structure, so it almost disappears in the sky, so I don't think you would be aware of the presence of this large structure.
It's somewhat like a screen in your window at home. You see right through the screen because the struts of the screen are very, very small, so it just looks to you as a window that you're looking through.
It will be so unobtrusive that city residents will give it no more thought than they once did of clouds passing overhead. The same clouds that are now outside the dome. Rain no longer drenches downtown Houston, but the sun hasn't gone away. Day after day, it beats down on those thousands of panels, dumping heat into the interior of the dome. Today's featured dish, Houston under glass. Skeptics argue that overheating is the dome's fatal flaw, but Fuller argued that just the opposite is true. Fuller called his domes chilling machines, self-cooling structures with little need for secondary cooling elements such as fans or air conditioners. The secret is in the way that the shape of the structure affects convection patterns.
You're going to find another built-in efficiency by the way air naturally flows in a spherical structure, and the larger that structure, the more you'll be able to take advantage of that relative efficiency.
As air heats, it rises. When it nears the apex, it cools and drops, causing the air to move in what's called a rolling donut pattern. This circulation prevents heat from building up at ground level. But Buckminster Fuller was prepared to go even further. He suggested adding adjustable vents at the top and bottom to further regulate temperature, keeping his dome warm in the winter and cool in the summer. But Fuller's idea was only an educated guess.
We've never done any real experiments of a large, dome to see whether that actually happens or not. It was a very nice diagram that Bucky made. It made a lot of sense, in terms of what he was saying, that actually would take place is something that I wasn't too sure about.
No large-scale test was available until 2001.
We don't have any air conditioning units to cool either of the biomes. They are only cooled through natural ventilation. We have vents in both the top and the bottom, and that's the only mechanism we use for cooling the biomes.
In Cornwall, temperatures average about 37 degrees during the winter. But one biome is kept at a tropical 90 degrees with plenty of humidity. The other at a desert dry 77 degrees. In Houston, vents located 1,500 feet above city streets will be rigged to open automatically when the temperature inside the dome rises. The vents will create a reverse chimney effect, pulling air in from the outside at the top where it's cooler. As it falls, it's forced out of vents near the base, circulating cool air through the dome. Properly calibrated, the system may also reduce Houston's killer humidity. Fuller believed that the vents would allow a dome's interior to maintain a temperature about 15% lower than the temperature outside, dramatically reducing the need for costly air conditioning.
You could arguably say that Bucky was the first green architect.
Fuller, back in the 60s and 70s, was not talking about climate change, but he was talking about sustainability. So he was an early environmentalist, I guess. And certainly that example points to the fact that the patterns we see now and interpret as such a surprising development were anticipatable a long time ago.
But the environmental efficiencies of the dome are tempered by one fact. Maintaining nearly 150,000 inflatable cushions at a constant pressure takes energy, and lots of it. But the dome offers a perfect solution. Thousands of solar panels, perfectly arrayed to track Houston's famously persistent sunlight. With little need for air conditioning, residents will experience a new city. But heat isn't Houston's only foe.
Good morning, Houston. Hurricane Sonia is still pounding away at the suburbs. We're expecting she'll work her way up to a Category 2 hurricane with winds up to 102 miles per hour and 6 to 9 inches of rain. Of course, if you are in the dome, you're in luck. It'll be another beautiful day, a carefully regulated 72 degrees and just 10% humidity, which is why I advise, don't leave the dome.
Obviously, one has to think a lot about social consequences of covering a city like Houston, where all of a sudden you are coming into a position where you can actually drive the climate.
I think the weather would be pleasant all the time. So one might miss the unpleasant weather. One might miss the joy of that first beautiful day in the spring, or the day when it finally stops raining, when it's been raining for a week in a row.
But of course, it would only be a matter of time until the dome would face the ultimate test. A Category 5 hurricane, bearing down with all its deadly fury. After years of construction, after billions of dollars spent, the Houston Dome faces its biggest test.
We need to consider protection against extreme weather events. And I'm talking about hurricanes.
A Category 5 hurricane can flatten the city, and when such a storm eventually bears down on Houston, the geodesic dome's most beautiful design features, the sleek steel struts, the lightweight plastic panels, and the absence of interfering interior support columns, may lead residents to ask, will this delicate-looking structure be strong enough to stand up to Mother Nature's worst? Against a powerful hurricane, the Houston Dome has several lines of defense. The first comes from its skin.
High winds for ETFE cladding systems not a problem at all, due to the material being extremely elastic and forgiving. They cope with basically any type of wind load if designed correctly.
ETFE can withstand winds of 180 miles per hour, a higher velocity than even the strongest Category 5 hurricane. The pillows have an added layer of protection.
It has an exterior layer, an inner layer, and an interior layer. As long as you can keep one of them, the whole skin of the dome still remains intact.
Even if a panel ripped wide open, the rest of the dome's steel frame would be ready to bear the burden. But the panel's ability to resist the buffeting winds is only the beginning. Behind them stands a second line of defense.
Mega structure of the kind that we're talking about for Houston, Texas. First of all, we have to realize that it's a space frame, which is a three-way grid.
The space frame, relying on the inherent stability of the triangle, provides a counterforce equal to any external wind load.
So now we have a very strong triangulated spherical structure, and it will not be vulnerable to the toughest hurricanes that we've ever experienced.
The dome is designed to take punishment. In a rectangular structure, stress is borne by relatively few supporting elements. Remove one, and the rest are overwhelmed. But a geodesic dome, like the dome over Houston, has thousands, in fact, hundreds of thousands of supporting elements.
The other thing about the geodesic dome is that the geometry allows it to have a great deal of inherent redundancies, so that I can actually come along and take out some of the struts, and the entire structure will still be incredibly stable.
Even when one strut is removed, the load it bears is redistributed. Removing dozens, hundreds, or even thousands sends the load in new directions.
So in order for a dome to really lose its effectiveness, you probably need to lose 20% of its components.
With over 369,000 steel struts in the frame, nearly 74,000 of them could fail before the dome would be compromised. Compared to the level of destruction brought by hurricanes today, it would be a small price to pay.
The cost of cleaning up and repairing every single building and house versus the cost of having to repair or restore the dome after a major hurricane, I think the advantages are with the dome.
That strength could turn hurricane preparedness on its ear.
Which is an irony in most hurricane situations. Everybody's trying to quickly get out of the city. Now we can imagine them quickly trying to get in the city and being safe.
Houston will set the standard for a new achievement in engineering, construction, and human ingenuity.
If it was built, it would give us a very different world that we would be living in, so it could have a huge impact, and that's important for us all.
As man seeks protection from climate change and faces an ever-changing world, cities could find new hope in a simple, strong, and soaring